Okay, if you remember last time, we had just introduced halohydrins as a precursor to forming epoxides because we were talking about preparations of epoxides before we moved into talking about their reactivity. And so if you remember, we reviewed the fact that we knew how to make halohydrin compounds from last semester where we simply took an alkene and reacted it with the halide in water, which gave the halohydrin. We said it was Markovnikov addition in an anti-mat manner, which gave these two substituents then in a trans orientation, which lined up for them being treated with base and basically doing a Williamson ether synthesis that was intramolecular within the same molecule that gave the epoxide. And so I promised that we'd start here. And so we want to just look kind of briefly at what the mechanism is. And of course, we know that mechanism because it's the same as the Williamson ether synthesis, but just to make sure, let's work through it. So the mechanism would be having the halohydrin, and I'm going to show the example, as an acyclic halohydrin. And we'll also have an R group here. So these two R groups could either be connected together to form a ring or just an acyclic halohydrin. It doesn't matter. And then we're going to treat that with our base, sodium hydroxide. And basically the base is going to take off our acidic proton, move the electrons to that oxygen. So the intermediate that would form would basically be the alkoxide there, still have my bromine. I'm keeping the stereochemistry I drew before. Okay, so you'd form that intermediate. Then this is my nucleophile. It reacts with the electrophilic carbon of the halohydrin, in a manner where it's coming from the opposite side of the halide, kicking it off as the leading group. And so the result of that is going to be the formation of the epoxide. And notice that the stereochemistry is going to be preserved. So if there is a cyclic system here, that stereochemistry is preserved. And you're also going to have sodium bromide as the byproduct. So this again is simply an intramolecular Williamson ether synthesis. Okay. Now just be aware, as I said, it can be cyclic or acyclic that this works on. So just to give you an example of an acyclic formation, you can do it actually to not only form epoxides, but you can do it to form ethers. So let's just say we have this compound. We could treat it with base, and it's going to pull off this proton, just like we saw with the halohydrin where we had the vicinal arrangement of the two functionalities. Here, they can be on either end of this molecule. Treat that with base. It's going to form that alkoxide, which then can close in. You have your leaving group, and you form your cyclic ether. Okay, and so we can use the same reaction to form cyclic ethers, the same as forming epoxides. Okay, and so once we formed our epoxide, then what kinds of reactions can they undergo? So reactions of epoxides. Okay, and it's basically, these are all going to be ring opening reactions. So we're going to be cleaving open the epoxide ring. Okay, and so the first of these we're going to talk about is what happens when you treat an epoxide with a dilute acid. So just a way of saying a weaker acid, and it's going to be aqueous. And this is a review. We've talked about this reaction already last semester. It was one of our synthetic utility reactions. This is reappearing. And that is we can take this epoxide, and by the way, this is probably how it looks on your flashcard from last semester. You treat the epoxide with an aqueous acid, and the result is the diol, like this. And since I used just the simple ethylene version of this, that is how the product would look. Okay? Do you remember this reaction? Let's look at a different example of it and see if you can come up with the mechanism. So let's say that we have this epoxide, and I'm using this one because I want to demonstrate the stereochemistry. Regiochemistry here isn't important because I'm ending up with an OH on both of the carbons, right? And so what's going to happen when I put this epoxide in the presence of an acid? We've seen this a million times now. O is nucleophile, reacts with the electrophilic proton on the H3O plus, moving the electrons out to the oxygen. And so the intermediate that forms is going to be this. You're also forming water. Okay, now what's going to happen? Well, now I have this oxygen I've protonated, making it more electronegative, and so that means I have electrophilic carbons here, and so water is going to act as the nucleophile, come in and react in an anti-manner to this bridged oxygen, breaking this bond, moving the electrons out. And so the result of that is still an intermediate, because what I'm adding neutral water, remember, and I'm adding it from below, because it adds in an anti-manner. Okay, and remember it also adds Markovnikov. We remember that from last semester. And so I end up with this intermediate, right? And then I've got plenty of water around. So water is just going to come in and take that proton off, move these electrons in. And so the resulting product is this trans diol. And remember, this was the complementary reaction to hydroxylation, where you had an alkene and you used osmium tetroxide, remember, or potassium permanganate, and you added the two OHs in a syn manner, and so you got the cis diol. So we've seen this reaction before, very straightforward. Okay? Now what happens if we alter this reaction to take advantage of this intermediate that's forming? And I'm going to erase everything but this intermediate, because all of us immediately recognized that this protonated epoxide is basically the reactive equivalent of a bromonium ion, something that we saw, or a chlorinium ion, where we had this Markovnikov anti-addition of nucleophiles that could occur on that bromonium ion, either another bromine or a water. Remember that reaction? Well, we have the same kind of reactivity here, so we can take advantage of that. So instead of treating it with an aqueous, dilute acid, another thing that you can do with an epoxide is open it with an anhydrous HX. Okay, anhydrous meaning now we're not going to have any water present. So that's going to change the nature of the reaction. It's still an acid. Okay, so we're going to take, in a general sense, if we have this epoxide and we react it with some HX, and it's going to be most commonly HCl or HBr. So I'll write that down. And then basically what's going to happen is what? You're going to open this epoxide. So you'll have the OH, but you're also going to have the X, which is the nucleophile that comes in. So this again is the synthetic opposite of the first reaction we looked at today. The halohydrin, where I had a halohydrin and I was able to convert it into the epoxide. Well, now here's the reaction where you take the epoxide and you open it up into the halohydrin. Okay, these things are simple now, right? Okay, so how is this going to happen? And by the way, Cl and Br are the most common, but you can use F and I also. They work. Just don't see them as commonly. So any of the halides will work. Okay, so mechanistically, what's happening here? It's not going to be anything dramatic, right? Because I have my epoxide. I'm going to write mechanism here. I have my epoxide. I'm reacting it with, and let's say HBr. Let's use a specific case. Remember what happens when you have an epoxide in the presence of an acid? This is the nucleophile, reacts with the electrophilic proton, kicks the electrons out here. We've seen this little mechanism so many times. Certainly we can remember it as we protonate the epoxide and we form that intermediate that looks very much like the bromonium ion, which we've seen even last semester, and we have the Br minus that was produced here. It's a nucleophile that comes in and reacts at that electrophilic carbon, breaks open that bond, moving the electrons out to the oxygen, and I end up then forming the halohydrin. And notice that what we learned last semester is this was anti and Markovnikov. So anti in terms of stereo, Markovnikov in terms of regiochemistry. All right. Now, another way you can open this ring, you notice these two examples we've just looked at have been acidic conditions. Either a dilute aqueous acid or an anhydrous mineral acid. But what happens if you open this with a base? So different conditions, you can still open it, okay? And so, simple example of that, just look at this epoxide. I'm going to draw it like this, and then I'm going to put in my OH minus. So if you have a base, it's going to be something like sodium hydroxide, potassium hydroxide. So you're going to have the hydroxide. If you want to put a counter ion there, let's put that. And then what's going to happen in this reaction? The base is going to act as a nucleophile. It's going to come in and react with the electrophilic carbon of the epoxide. It's going to break this bond and move the electrons out to the oxygen. So you can see it's occurring, in a very similar way. The only difference between this and the acid is I didn't protonate that oxygen first because there's no acid. So the base is acting directly with that electrophilic carbon, and so the intermediate that's forming is this. Okay, and then what's going to happen? Well, I have water present because this is an aqueous base. So the oxygen is going to take a proton off of water, kick the electrons out to that oxygen, and so the final product, I will have protonated this oxygen, and I form the diol, okay? But I also reform OH minus. So just like we saw in the previous case, this is base catalyzed. The other was acid catalyzed. Okay, so that's one way you can open it with an OH minus. So under basic conditions, you open the epoxide. You again get the diol. Okay, but you can also, another basic thing that we've looked at is a Grignard. Grignard reagents, remember, were the carbon nucleophile reagents, the organometallics. They will react also under basic conditions. Okay, so again, let's look at a simple epoxide like ethylene oxide, and we're going to react it with a Grignard. Let's just use a simple methyl Grignard, And what's going to happen here is, again, this, remember, reacts as an R minus. So this is a nucleophile, reacts with the electrophilic carbon of the epoxide, breaks open the bond. So that C to O bond is broken, which means that I will have the, let's do it mechanistically. We form that O minus there, and then we also have our Grignard, and then you just need, remember with Grignards you always do what? An acid workup. And so then this is able to pull the proton off of that, kick the electrons out to there, and you have formed, and I'm going to write it out like this. You have now formed your product, okay? Which now you've added basically as many carbons as you have in the R group at the Grignard. You're essentially adding that many carbons to the epoxide, and you're leaving that OH functionality. So you can think synthetically how that might be important. But if you noticed in the previous example, and it's not, I didn't show it here, but the regiochemistry of this, for the acid ring opening for the epoxide, we said that it was Markovnikov and anti-addition. Okay, but what about the regiochemistry here? We really need to look at this regiochemistry of epoxide openings, because we're going to see they're not exactly the same depending on whether you're doing acid or base ring opening. Okay, so let's call this regiochemistry of epoxide opening. Okay, and it depends on the conditions. So first, let's talk about base conditions, because believe it or not, that's the easiest one. So if you're opening an epoxide and you're using basic conditions, so those are the last two reactions really we're looking at. You use sodium hydroxide as one example, or using the Grignard. Those are both opening epoxides under basic conditions. Okay, if that's the case, you have a basic nucleophile that is doing the opening, and it's then simply an SN2 type reaction. So it's governed by the same conditions and characteristics that we've talked about with SN2. Okay, and so that means that the nucleophile goes to the less substituted side, because it is less sterically hindered. Okay, and so an example to illustrate that is, here's my epoxide, and I'm going to put some substituents on it. Let's put an ethyl group there and a hydrogen. And then on this side, I'm just going to put two hydrogens. Okay, so when you're analyzing the regiochemistry of this opening, and you're going to have a nucleophile that's going to open it, and under basic conditions, you know, let's, instead of using OH minus, let's use OR minus. That's still a good, that's a base, right? And it's also a good nucleophile. It's from SN2 reactions last semester, we know this is a good nucleophile. So this will open the epoxide. Okay, but the question is, when this nucleophile comes in to react, it's either going to react here or here. That the regiochemistry is determined by that. And if it's SN2-like, this position, that is a primary carbon, right? Because there's only one carbon attached to it. This one is secondary because there's 2 carbons attached. So which of these is the less hindered site? Which one is going to be favored by SN2 conditions? It's going to be coming into the less hindered side. And then it's going to break this bond, electrons moving up to the oxygen, right? And so the result of that is going to be the addition of the OCH3 to this side, okay? And so again, the end product, we don't have to look at it mechanistically, the end product is going to be what? We're going to have my OCH3 adding to this carbon. So I'm going to end up with that product. OH ends up on this carbon because when it opens up, oxygen ends up here. The nucleophile that's adding, the OCH3, comes into the less substituted side. And so that is the product that we get in terms of regiochemistry. Now, if we do this opening under acidic conditions, the results are a little different. Okay, and because we've already seen, we said that it resembled the bromonium ion, and so all of the regio and stereochemistry is the same as it was for a bromonium ion. But you may not, that was last semester, and we said it's Markovnikov addition. That's the regiochemistry, and anti-addition is the stereochemistry. But do you remember how we explained it? It's not that it's straightforward SN2. And it's not that it's straightforward SN1. It's actually a combination. And so it has SN1 and SN2 characteristics. Okay, and so when you're doing an acidic opening, we're going to see that both of these different substitutions, their characteristics are applied to this opening. And it's basically because the regiochemistry is actually SN1-like. So that means the nucleophile is going to go to the more substituted side. And we saw that, right, when we were opening bromonium ions. We're going to have SN2 stereochemistry, which means that the nucleophile is always going to come, there's not a mixture in terms of stereochemistry. Nucleophile is always going to come from the opposite side, the inline mechanism. Comes in 180 degrees from the leaving group. Okay, so those characteristics are going to come into play. So let's see how that would look when we actually do it on an epoxide. So again, I'll use an example of an epoxide. Let's put a methyl group on this side, and let's put just hydrogens on this side. Okay, and then I'm going to react this with HCl, and I'm going to put ether here as the solvent because I'm emphasizing the fact that this is not aqueous. This is that anhydrous HX that we talked about. No water present. HCl and ether. Okay? And so we know what happens, right? Initially, mechanistically, this oxygen is going to take the proton and form that intermediate where this oxygen is protonated. So the question we're asking here is the chlorine then, when the chlorine comes in to react, is it going to react with this center or this center? These are the two electrophilic carbons, okay? But if the regiochemistry is SN1-like, it is going to go to the more substituted side, okay? Because remember, when you're looking at partial charges here, because this is electronegative, these two carbons are electrophilic, so they've got a partial positive charge. Well, the one that's more substituted has more stabilized positive charge character. Therefore, the nucleophile in the acidic case comes into this side. Okay? Opposite regiochemistry to the base opening. And so therefore, when we look at our product, it's going to be what? We're going to look at the fact that the Cl is going to come into this side, right? and so then the OH ends up on that side. And the selectivity here is about 90%. You know, it's not regioselective, but it's about 90%. So that means you really don't have to show the other possibility. Okay? And so when you're looking at these epoxide openings, basic conditions, totally SN2-like. Acidic conditions, it's SN2 in terms of stereochemistry, but it's SN1 in terms of regiochemistry, okay? And so a good example to demonstrate that, which would be a synthetic example, when you're trying to work through these two things, I think it's always good to have a side-by-side comparison. So let's look at a synthetic case that will demonstrate this. Let's say that we have this epoxide, which we formed from our famous example of an alkene for our flashcards. And that was, I started with the alkene where I had the double bond in the methyl group, right? So I'm going to form this epoxide. And the reason I'm using this example, so this is a good one to maybe, you know, put an asterisk by for you to look at, because it's going to explain the regio and stereochemistry of these two different types of openings depending on conditions. And so if I take this and I treat it with ethanol in the presence of acid, so I'm doing a ring opening because I have a nucleophile, and I'm doing it under acidic conditions. And so what's going to happen is I'm going to add this OR group, okay? But since it's acidic conditions, the regiochemistry is going to be SN1, stereochemistry is going to be SN2. So that means that when I look at the product, the nucleophile is going to go to the more substituted side, and it's going to come in from the opposite side of what was the epoxide oxygen. Okay, so regiochemistry to the more substituted side, that's SN1. Stereochemistry is SN2 because this comes in from the opposite side of the oxygen that was the epoxide. So you see that? Acidic conditions. Now take the same epoxide, formed again from that same alkene we liked from our flashcards last semester, but now I'm going to react it with the ethoxide. So this is going to be under basic conditions. So I'll put the charges in there if that helps. Okay, so now it's going to be totally SN2. So that means that in terms of regiochemistry, my nucleophile is going to go to the less substituted side, but it's going to do it from the opposite side of the epoxide oxygen. So therefore, the product that forms is going to be this. Right? And then my epoxide oxygen is here, which means my methyl group is there. And so notice that the stereochemistry between these two groups is the same because it's both SN2. The difference is the regiochemistry. More substituted, less substituted. SN1, SN2. Okay? That's basically everything we want to talk about with epoxides and their reactions. But you can see it's a good way to, lead to complementary reactions where we're forming alcohol functionality, but also being able to add nucleophiles. So very useful reaction synthetically. Okay, but that brings us now, just as we did with alcohols and then we talked about thiols, now we want to talk briefly about sulfides. And sulfides, remember, are just the sulfur analogs of ethers. Okay? I'm going to write that down. The sulfur analog of ethers. And so we can assume that they're going to behave in a very similar manner because, structurally, all we're basically changing is the fact that we have two organic residues that are now attached to a sulfur instead of an oxygen. Okay? And so nomenclature for this is going to be exactly like what we saw for an ether. Subordinate functionality, so there are basically two ways we can do it. Remember the first way that we talked about doing ethers is that you could just look at the two residues and name them, the substituent name, and then you just added the suffix ether. Well, you can do that with sulfides too, but it's basically instead of putting ether as the parent, you're going to put sulfide. It's kind of a no-brainer, right? So, for example, if I had this sulfide, I would just name the two residues and then put the sulfide, the word sulfide at the end. Okay? And so this would be ethyl, right? Space methyl. Those are the two residues. And then the word sulfide. Ethyl methyl sulfide. Okay? Just naming the two residues. But just like we saw with ethers, if you have a more complicated system where you have multiple functionalities, and the sulfide then becomes a substituent name. Okay, so substituent. How would you name it as a substituent? And remember, with the ethers, we use the alkoxy nomenclature method. And that is where whatever the alkyl group is, you then just added oxy to the end of it, alkoxy. Now we're going to substitute that. So replaced with alkyl. I want to make sure that, thio. Alkyl thio. And so example of that, I'll use the same example that we did when we talked about the alkoxy substituent. Let me draw it like this. Say we have this system, we have a double bond there, we have a sulfur, and then we have a methyl. So similar system we saw. We have two organic residues on either side of this sulfur, but I want to name it as an alkene. And so then the sulfide functionality, I'm going to name it as a substituent. So again, I'm going to number like we learned for cyclic alkenes. And then the substituent is in the 4 position. And what is the substituent? It's methyl thio. Sorry, I'm still doing the dramatic pause for someone to answer, but I know there's no one here. Well, actually, my kids are not far from me here. They're not answering. 4-methyl-thio and then cyclohexene. And the 1 can be understood here just because of the IUPAC rules, but if you wanted to put the 1 in there, you could. Okay, so methyl-thio is how we would name that. Whatever your R group is, the alkyl group, you just substitute it in front of the thio. All right, so nomenclature, not very difficult there. So once we know how to name sulfides, then we can talk about reactions they undergo. But before we do that, we need to talk about preparation. So how am I going to prepare a sulfide? Well, the first way you might think is the same thing we talked about with ethers, and that is if you had this as a nucleophile, and I'll put a counter on there, this is called a thiolate. And thiolates are nucleophiles. They're just like OR groups. So good nucleophiles. And so I should be able to react that, right? Just like we saw with the Williamson ether synthesis. We should be able to take this and react it with an alkyl halide. Okay, nucleophile reacts with the electrophilic carbon, displaces the electrons over to the leaving group, and you should be able to form this sulfide, like that. Okay, and this reaction does work. Okay, but the nice thing is it works for primary and secondary. So unlike the Williamson ether synthesis, it only worked on primary alkyl halides. Here we can actually use secondary and it still works. And that's because a sulfur is more nucleophilic. Remember when we talked about nucleophilicity, we talked about the fact that the nucleophilicity generally as a trend increased as you went down the column of on the periodic table. Okay? The electrons on the sulfur are farther from the nucleus, a little more polarizable, so more nucleophilic. Okay? So the reactivity is a little better. You can do it on primary and secondary. Okay? That is the best way of making sulfides. Okay? Once you make them, what reactions do they undergo? So reactions of sulfides. And they're not going to be a lot here, but the basic thing to take home is that sulfides, as we just saw, are more nucleophilic than ethers. So that sulfur group is more nucleophilic because, as I said, it's more polarizable. Electrons are farther from the nucleus of the atom. And so therefore, if we look at a comparison here, if we have this ether and we try to react it with an alkyl halide to see if this acts as a nucleophile and can actually then alkylate the oxygen, this reaction does not work. You can't do it. Okay? However, if you take the same kind of system where you have a sulfide and you react it with an alkyl halide, where this would be the nucleophile reacting out with the electrophilic carbon of the alkyl halide, pushing these electrons out, that actually does occur. So if you add another equivalent of alkyl halide to the thiolate addition to make the sulfide, if you put another alkyl halide in there, you can form this group. Okay? And it's basically forming a salt because I'm going to have this I- as the counter ion. Okay? And so this actually is a useful reagent for synthesis. So it's something you can form because this is more nucleophilic. And I formed this salt, which is an alkyl sulfonium salt. Let me write that down. And we're going to see how we can use this synthetically. Okay? And so I'll show you an example that's a specific example. And also to let you know that this is chemistry that is done in the body when your body does alkylation reactions. This is how the body does it. So it's a biological reaction also. So you have a sulfide, and I'm going to react this with methyl iodide. Okay? And so it has a nucleophile. It's going to do the substitution. So that extra methyl group is going to go on. I have the two methyls that are already there. So this has a plus charge, and I have my counter ion, which is the I-. Now, what is the reactivity of this? Now I have these three alkyl groups, and I have this electronegative atom, a sulfur, and I've given it a plus charge. That means inductively, I have bond polarity here where the sulfur is pulling electron density away from these alkyl groups. They all become partially positive. So they're all becoming electrophilic. So that means I can take a nucleophile and it will react with one of the alkyl groups, kick the electrons back to the sulfur. And so one of the things you will get is you will recover your sulfide, and then your nucleophile is going to be alkylated. And so let's think for a minute, because I know a lot of us out there are biology majors or have some interest in biology. Why would this be a reaction that the body could use to do alkylations? Well, because if you can imagine an amino acid, for example, maybe that has a sulfide functionality, or other molecules, if you're alkylating them to form a salt like this, then you can alkylate something else in the body and you recover the sulfide. So this sulfide keeps being regenerated. Reactions in the body, you don't want to destroy compounds as reactions are occurring. You always want them to be regenerated. So this reaction is not only good synthetically in the lab, but it's also what happens in the body when you do alkylations. Now, what do you think is one restraint that would be required? If you're wanting to alkylate your nucleophile, so it's going to react with one of these three alkyl groups. When you're doing the reaction, whatever alkyl group you're wanting to alkylate onto the nucleophile, all three of these attached to the sulfur need to be the same alkyl group. Why? Because then you don't get mixtures. Because this nucleophile could react here, here, or here. So you always want it to be like trimethyl, triethyl, tripropyl, tributyl. You always want all three R groups to be the same, so there's no mixture of products. Okay? So that's a useful application of a reaction of sulfides. But the other thing that you can do with sulfides are oxidation reactions. Okay, and so you can oxidize these. And if I have a sulfide like this, I can oxidize it. Remember when we were using the terms oxidation and reduction. In organic chemistry, when you oxidize something, you're basically adding oxygen to it. If you're reducing it, you're usually adding H. I should say oxidation, you can also be adding things like bromines, things besides H. So when I take this and oxidize it, I can take something like hydrogen peroxide, which is almost always aqueous, and this will happen at room temperature. So peroxide treated with a sulfide will actually oxidize this to the sulfoxide. And this is a functionality that we learned when we were talking about functional groups. Okay, you can also sometimes see this sulfoxide drawn like this. Sorry, it's S. Where you're showing the resonance form of this, where there's a plus and a minus and a single bond between the sulfur and the, they're the same thing. They're just different resonance forms. But this is a sulfoxide, okay? But sulfur has different oxidation states. So I can take the same sulfide, but I can treat it with a different oxidizer, peroxy acid. Remember, that's the reagent that formed epoxides. but it's also a stronger oxidizer than just hydrogen peroxide, peroxy acid. That will oxidize the sulfur up to a higher oxidation state. Which is called the sulfone. Again, that's a functionality we learned last semester. So these are both oxidations. It's what oxidation level you're oxidizing to. Hydrogen peroxide to the sulfoxide, peroxy acid to the sulfone. Okay? And those are basically the only reactions for sulfides. So at the point we've reached right now, we have finished our discussion of alcohols, thiols, ethers, and sulfides, all functionalities that are somewhat related in reactivity. And we've talked, about several really good synthetic utility reactions for them. Okay? And so now we're about to do a major shift in focus because we're about to start talking about the last set of functional groups for the semester, and that is we're going to start talking about the carbonyl compounds. Okay, and so what I want to stress at this point, I know we've been talking today for just short of 50 minutes, but since the lectures I've been recording and putting on Moodle, I've been assigning dates to them, but the dates aren't quite as important. Like, for example, I apologize that I dated one Good Friday. And, I'm just assuming that I'm putting these lectures up and you're watching them whenever you can. So I'm not saying that hopefully you didn't sit there on Good Friday and feel like you had to watch a lecture. But I'm not as concerned about lectures being assigned to certain days, just to topics. And so some of these lectures may run a little longer than others because I'm going to stop here in a second because the next lecture we're going to do an overview of carbonyl compounds. So I'm going to talk about something that's going to be reviewed from a week ago, and that is there are really two kinds of carbonyls: ketones and aldehydes, and everything else. Ketones and aldehydes do addition reactions. The other carbonyl compounds do substitution reactions, and that's basically because ketones and aldehydes don't have leaving groups attached to them, everything else does. And so what we're going to find out is from here on out till the end of the semester, only two reactions, either addition or substitution. And so looking at the big picture, that's what you're looking for, is we're going to look at 75 reactions, but they're going to fall into one or two categories. And so it's actually pretty straightforward. But you need to go in with that assumption. So what we've already seen, remember when we talked about Grignards reacting with carbonyls in the alcohol section? We said that it did addition with ketones and aldehydes, but then it did substitution initially with the carboxylic acid or ester or acid chloride. That's basically, in a nutshell, the rest of the semester. Every reaction is going to be either on aldehydes or ketones giving one result, or with carboxylic acid derivatives, those other things that give substitution. Okay, so next lecture is just going to be an overview of carbonyl compounds. Then we're going to start breaking them down. We're going to talk about aldehydes and ketones, and then carboxylic acids, and then we'll get to the other functionalities, pretty much one at a time. All right? So till next time.